Hello everybody and welcome to session 3 of the um, InfoDrainage modeling training course. This session starts immediately after session 2, so if you're continuing to work through them in order you can just carry on. If not, you'll only need to open the file exercise 2 in the answers directory of the InfoDrainage introduction. This session is all about pipe design, and the first thing to focus on is the fact that it is purely sizing of pipes and placing them at the correct depth and distance, correct depth and gradient below the ground. We haven't begun to talk about the design of storage or SuDS, BMP, LID features, anything like that. This is purely focused on pipe design. And the pipe design is conducted in accordance with UK standards, so that's the DCG, Design and Construction Guidance, which followed on from the old SuDS for adoption, the different stages of that. And that design guidance in particular sets out pipe design as a two-stage process. And it is important to recognise that there are two very separate stages to this. Stage 1 is where we design for a no surcharge criteria. Now that is simply saying that the pipes don't become more than full, so there's always a free surface within the pipes. The pipe capacity is greater than the flow rate. Now that first stage, that no surcharge, is typically done according to the DCG for storms of fairly low return period. 1 in 1 or 1 in 2 is common, 1 in 5 is less common, but it's going to be one of those three types of return period. And the important thing about that as well is that it's essentially a steady state. So the software calculates what the steady state flow will be and then simply sizes the pipes and puts them at an appropriate gradient so that their capacity exceeds the flow that's being tested. So it's a steady state calculation. There's then the second stage, or the second criteria, that these pipes must fulfill. And that criteria is a no flood criteria. So that's during a higher return period storm, typically a 1 in 30 year storm. We are meant to design the pipes such that they don't flood. Now this is a dynamic simulation. Here each storm has a sort of start, a middle and an end, and we have to run that through dynamically to see the pipes. The pipes are allowed to fill up, the manholes are allowed to fill up as well and then drain down, so long as at no point is there flooding on the catchment surface. So we've got this, essentially the process is run the no surcharge test and we size and gradient the pipes based on that, and then in the second stage we check them to ensure that during these larger storms that there is no flooding. And as I said, that requires a different type of analysis. It's a dynamic volumetric analysis as opposed to the no surcharge case, the first case, which is a steady state analysis. Okay, so we're going to go through, the stages have to be done in order. You have to do the no surcharge first and then the no flood. So we're going to go through section 3.1, the no surcharge criteria as well. Sorry, no surcharge criteria first. Okay, so to do that, you've got the model open. Go to the preliminary sizing. And what we're looking for first is the network design criteria. So this is simply asking us what type of storm is going to constitute our no surcharge criteria. Now we're going to need to first set up some storms. So actually I'm going to come out of here first and I'm going to go into my rainfall stroke pollutants, and in there is a rainfall manager. Now this is where we create all of our storms, whether it's for the no surcharge test or the no flood test. They're all created in this dialog box here. So we can see that there are, under the design storms, there are basically three types of design storms. FSR and FEH are the common design processes used in the UK. FSR stands for Flood Studies Report, FEH, Flood Estimation Handbook. I'm not going to go into the details of which one of these you should pick and how they should be defined and all that kind of stuff today. I will simply say that FEH is the more modern, the more comprehensive. It is available, the data associated with it is available to purchase from CEH, Centre for Ecology and Hydrology, Wallingford Hydro Systems, they sell that data. So for that reason and that reason only, because this is a recorded training course, I want to use data that's freely available. We're going to use the older rainfall today. However, again, just to reiterate, there's no difference in the process here. There's no difference in how we go about this work, but just be aware that we're using an older rainfall theory to size these pipes. Okay, purely, as I said, because it's free. If you're working outside of the UK, currently you have to use this user-defined rainfall, and I'm not going to cover this on the course today. We'll do a separate section purely about that. And over time, hopefully, we intend to put in other rainfall theories from around the world. But at the moment, FSR and FEH are purely UK based. We've also got this known rainfall, which is where you could take a particular observed storm and put that through your network to see if it causes flooding or not. But like I say, today we're going to focus on design storms. So the first thing you do is pick your design storm, in this case FSR, the old data type, add it in, give it a label. So I'm going to call it, rain 1. And we're going to test for both summer and winter. As I said, I'm not going to go into the details of the theory, but in some cases, summer storms could be your worst. They tend to be the short, intense storms, or it could be winter the storms, the longer, higher volume events. So the point is that when we do this type of analysis, we have to cover all options. We have to cover summer and winter profiles and long and short storms. I'm just going to put in some arbitrary parameters. These parameters are based around sort of Oxford, Swindon, South UK type parameters. But as I said, we just need some rainfall. This course is not about explaining rainfall theory. Also going to set up some return periods. The first one, as I said, is for the no surcharge case. So we're just going to go for a 1 in 2 years set of storms. There's going to be no climate change allowance. That's again in accordance with the DCG guidance. So at these low return period storms, the guidance is that we don't need a climate change allowance for that. Now under the storm durations, some people would pick all durations and test with all storms. Personally, I think it's enough to use the default range of storms. So you can see here we've got all storms from very short 15 minutes through to very long, up to 1 day, 24 hours in duration. And in some catchments it's going to be those short storms which cause the worst problems, and in other catchments it's going to be the longer, higher volume storms. So the important point is that we have to test a range of storms. Now, InfoDrainage has the ability to save the rainfall separately from the catchment data. The advantage of that is that we've seen, as I just explained, with other types of data, you have to buy that data, not from us, but from a separate company, completely independent from us. You have to buy that data, bring it in. And the thinking here was that if you are conducting several studies which are very close together, you can create just one rainfall event and then use that across different studies. So that's what we're going to do here. We're going to save that data. I'm going to put it in my save work here directory, and I'm going to call it design rainfall. Okay, and save that. And then if we were working on a similar study close by, we could just load that data in and call it from there. Okay, so that's the advantage of saving the rainfall separately to the catchment data. Okay, so I've created my rainfall. Now going back to this preliminary sizing and go into the network design criteria. So this is essentially the rules under which we are going to design these pipes. So I could have created my rainfall at this stage. I chose to do it separately, but it's exactly the same data, exactly the same thing that I'm creating. And now I can pick that rain one from the library, and you can see it brings in the same parameters that I just specified, the return period. We have also as well this minimum time of entry and maximum time of travel. Time of entry is the time that it takes the rainfall to run across the catchment surface and enter the nearest manhole. And we talked in exercise 2 about how we create these catchment boundaries and decide which areas are going to drain to which manholes. So it's that time delay. There's guidance on this in the Wallingford procedure, We're going to stick with the default of 5 minutes from here. And maximum time of travel is 30 minutes. We are using the modified rational method to design these pipes, and that theory is bound up with a time of travel. And 30 minutes is plenty. When it comes to designing these pipes, even for some of the largest housing developments that we may work on, it's very unlikely that the water would take more than 30 minutes to flow through the pipes and out of the outfall. Remember, we haven't started introducing storage or substructures yet, so purely through the pipes, 30 minutes is plenty for that. Okay, so that's essentially the inflows. We've digitized our catchment boundaries, and in conjunction with this rainfall that we've just specified, we will end up with some calculated flows, and on the basis of those flows, we're going to design the pipes. And here under the Design Options tab, it talks about the rules under which those pipes will be designed. So we are first asked to specify a library of pipe sizes. And typically in the UK, we would start at 100 millimeters or 150 millimeters. Different authorities start from different minimum pipe sizes, but always if you start at 100, you then go up to 150 millimeters, and from there you go up in 75 millimeter increments. So 150, 225, 300, 375, 450, 525, etc., etc. Just getting bigger and bigger. In the US, you would go up at 3-inch intervals, so you start at 6-inch and then go up 9, 12, 15, etc., etc. So it's asking you which library do you want to pick from, and that's the default library, is going up in those 75mm increments. If you've got your own sizes, different sizes, you want to miss out some of those, you don't want to pick for the entire list, then you can customize your library, but that's the default one that it's going to pick. These lock slope options, I'm not going to go too much into the details. This is more advanced, but in most cases, you would want the software as much freedom as you can give it to set its own sizes and slopes, gradients of pipes correctly. Now, I must admit at this stage I've never worked on site, but people who have worked on site tell me it is simply easiest to lay pipes soffit to soffit rather than invert to invert. I'm going to go to a whiteboard now, or paint, just to show what we mean by that. So we're talking about, do we want to lay the pipe soffit to soffit up here or invert to invert? So do we want to get the bottoms the same or the tops the same? So what's happening is you've got a ground level like this, you've got a pipe coming down like this, and again, apologies for the terrible drawing, those should be straight. You come to a manhole here where the pipe is going to increase in size. And the question is it going to increase in size and keep the soffits level? So in other words, drop the inverts. Oops, again, terrible drawing. Or is it going to keep the inverts level and raise the soffits? That's your choice. The pipe's going to get bigger. Which one is it going to maintain? Is it going to maintain the top in this case, or is it going to maintain the bottom in this case? Well, the easiest way I'm told to build pipes is to keep the soffits level. So you go soffit to soffit. This minimum cover level is asking you simply how deep below the ground do you want to put the pipes. 1.2 meters is pretty standard. That comes from the DCG guidance again. You can change that globally, or you could change it for individual pipes if you need to. We looked at tables in section 2. Once you understand tables, you can edit values there. So for example, you may have some of your pipes are going below roads where you need to put the pipes at least 1.2 meters into the ground. If it's just, there's no roads, it's just walkways or open land, then in some situations just 0.6 meters can be sufficient. So like I say, you can specify it for all pipes here or customize it for each individual pipe. So once the flows have been calculated and the pipes have been put in the ground, it has to work out the size of those pipes and the gradient. Now we specify a minimum and maximum gradient, and it must stick in those bounds, but also the velocities can't be too low or too high. And both of these things are based around the fact that if velocities are too low, you tend to get siltation in the pipes. If they're very flat, you can get stagnant water, which is obviously not great. If the pipes are too steep, then you get fast flowing high velocities, which can cause damage. You know, it's going to hit into something eventually. So whatever it hits into, there's going to be some dissipation of energy and potentially some wearing of the infrastructure. So whether you use minimum maximum slope or minimum maximum velocity or both, that sets the limits of how flat and how steep the pipes are going to be. There's also an option here to allow backdrops. I know a lot of authorities don't allow backdrops. Again, I'll just very briefly explain what a backdrop is. So we have a situation here where you might have the ground level here. Actually, I'll draw it again. If you've got a very steep ground level, then perhaps you don't want the pipes running at a constant depth, because then you would exceed your slope or velocity criteria. So what you can do is, if you've got a manhole here, for example, you can have the pipes coming in at a higher level and then going out at a lower level, and that means that they don't need to be as steep as they otherwise would be, and that's called a backdrop. So some local authorities allow backdrops, others don't. By default, we've got it switched off. I don't think I need to go in too much into the options here. Normally you're going to be designing these pipes as long as they don't run completely full, and that's an acceptable criteria. You can change that limit if you need to. And just like the pipes, we would have a library of manhole sizes, and essentially what we're saying is the bigger the pipe, the bigger the manhole you need to house it. So again, it's just picking from a library on that basis. Okay, so I think we've got everything set up. So you press OK on that, and then you run through and run the sizing wizard. So we've got this network design wizard. Actually, before I do that, I just want to show you just a reminder. We saw this at the end of section 2, but once we've created a flow path, if we go into show profile, before we've done the design, we just did the basic model build, and the pipes by default were simply laid on the catchment surface. So that's our starting position. The sizes haven't been calculated, the gradients haven't been calculated. So that's our starting point. And now we go through the network design wizard. The first thing it's asking us is to define which flow path. So in our catchment, it's very, very simple. We've just got one branch, so we're obviously going to design that. But you can imagine in a more complex network with several branches, it can ask you just which areas of the pipes are you going to design in one go. So it's based on flow paths. So pick your flow path, click next. Here, this is the data we've already seen. This is asking us the rainfall, which is going to calculate the flow. So we've got the rainfall, we've got our catchment. Actually, one other thing I'll just show you at this stage is if we look at our catchment data, I'm just going to cancel this. If we look at our catchment data, so what it's saying is we've got the area, in this case 0.09 hectares, the rainfall is going to fall on that area. And in section 2, we spent some time explaining the importance of this percentage impervious, or PIMP value. The fact that of the rainfall which lands on the catchment, not all of it will make it into the nearest manhole. We only get runoff, we only get a contribution from 60% of the catchment area. But even then, even the rainfall that lands on the roads and roofs, the 60% of our tarmacked or concreted impervious area, even that doesn't all make it to the manhole. Some of it will evaporate back up, some of it will find its way to cracks in the pavement, that kind of thing. Some of it will run off and discharge to a system, but not the system that we're currently analysing, maybe a local watercourse or somewhere else. And there is a theory that around 75% of the rainfall that lands on that impermeable area makes it to the manhole. So we're taking the rainfall on 0.09 hectares, we're multiplying it by 60%, we're then multiplying it by 0.75, which overall gives us, I believe, 45% of the total rainfall that lands on this area. Simply multiply that by that, and that's our total contribution, and it's on that basis that the pipes are sized. Okay, so stepping through the wizard, there's our pipes, there's our rainfall, there's the rules under which we're going to design these pipes, and it goes away and it does those calculations. Okay, press finish, and it's resized the pipes. Now the first thing that is useful to check is that we now have a table. In one column here we have the capacity. So in other words, what it's saying is that we haven't got pipe diameter listed here. We can list it in another of the tables, but we've got a certain pipe size at a certain gradient will give us this capacity. And based on our rainfall and our contributing area and our pimp value and our volumetric runoff coefficient, we've got a certain flow. And it's useful to look at this table at this stage because we can see how close to the capacity are our current flows. So if we look at this first pipe will carry up to 28.2 litres a second, but our current flows are only 9.94 litres a second. In other words, we've got plenty of capacity in this first pipe. So if we were to build a few more houses, concrete or tarmac over a larger area here, it is likely that this first pipe would still be able to take those flows. As we move further down the system, we can see, particularly this pipe 2 listed here, the flow is really quite close to the capacity. So if we were to build some houses up here, this first pipe would probably be okay, but by the time we get to the second or third pipe here, it would be very, very close to the capacity. We can see then there's a big jump in capacity, and presumably we've then got a larger pipe size or a steeper gradient, but it's likely to be the larger pipe size. So if we now want to look at that, one of the best ways to look at that is through the profile. So we show the profile, and now we can see that the pipes are more sensibly placed under the ground, and we can actually zoom in, and you've got it listed there. So the first two pipes are 150, then it jumps up to a 225, so no surprise that the capacity went up quite substantially. Now we can see in this example that we've got a ground slope at the top here, and we've got the pipes laid here, and you can see the pipes are a lot deeper into the ground at the top than they are at the bottom. And that's because we could only lay them at a certain slope to meet either the slope criteria that we specified or the velocity criteria that we specified. So because of that, it's laid at a particular slope. Okay.